A hydrogenation of a carbon-carbon double or carbon-carbon triple bond is the one reaction that doesn't involve a polar molecule AB, non-polar hydrogen gas. Most of the reactions of alkenes and alkynes that we're going to be interested in involve a polar compound, such as hydrogen halide, HBr as an example, or water, which will result in hydrohalogenation and hydration, respectively. So we can take a carbon-carbon pi bond, like cyclopentane, and we can add either HBr or water across that pi bond to result in an alkyl bromide or an alcohol. In this case, since we're working with a symmetrical alkene, there's no stereochemistry, so it's not possible in this particular reaction to investigate the regiochemistry or the stereochemistry of the reaction. These reactions proceed through carbocation intermediates if done in water. So if we have aqueous hydrogen bromide, for example, or water with catalytic 98% sulfuric acid or dilute sulfuric acid, generally not more than 3 to 6 molar, we can effect these reactions. The mechanism is fairly simple. And it's effectively the reverse of the dehydration of alcohols, where in both cases hydronium ion is your source of a proton. The pi bond attacks the proton to generate the carbocation intermediate. And then the nucleophile bromide in the case of hydrohalogenation. Water in the case of hydration. Attacks the carbocation intermediate. In the case of the hydration process, there'll be a third step because our result of attacking the carbocation with water will still be positively charged and will need a proton transfer to regenerate the acid catalyst and generate the alcohol product. So step one, in both of these reactions, is protonation of the pi bond. Step two, in both of these reactions, is nucleophilic attack on the carbocation. And step three, in the hydration reaction, is a simple proton transfer to take the hydrogen off the alkyl oxonium ion and put it on water to form hydronium ion. This is a fairly simple mechanism, and they proceed through carbocation intermediates. That means that there'll be no stereospecificity. Because once you form a planar carbocation intermediate, the carbocation intermediate can be attacked from either side. But there will be regioselectivity in the case of an unsymmetrical alkene. Because the intermediate is a carbocation, if you start with an unsymmetrical alkene, you will have two possible carbocation intermediates, one of which is more substituted than the other, and therefore forms in larger quantity than the other. So for instance, we start with an alkyl group. Work with one pentyne. So we got a propyl group attached to one end, hydrogens on the other end. We have a vinyl group here. And we react this with aqueous acid. Aqueous HBr in this case, which we know immediately dissociates to form hydronium ion and bromide. We have two possible intermediates, one of which puts positive charge puts the positive charge at the one position. We know that the secondary carbocation is more stable. Than the primary carbocation. So we know that the major carbocation formed will be the one that puts the carbocation in the secondary position, and thus the electrophile, which in the case of any reaction involving the hydronium ion, ends up at the less substituted end. And the electrophile always ends up at the less substituted end. When there's a difference. There are no exceptions to that rule. The electrophile always ends up at the less substituted end because the positive or partially positive charge always wants to be at the position that has the largest amount of stabilization by hyperconjugation. When bromide comes in, then it will primarily attack at the 2 position, and we will end up with, as a major product, two bromo pentane rather than the corresponding 1 bromopentane. This is not a stereo-specific reaction, or sorry, a regio-specific reaction. It is theoretically possible for the primary carbocation to form. This is a regio-selective reaction. The secondary carbocation is lower energy, and therefore the transition state is lower energy, and so the 2 bromopentane is preferred, but for energetic reasons, not for any reason that excludes the 1 bromopentane from being formed because of the mechanism. This process is referred to as a Markovnikov addition. Where it follows the Markovnikov rule, where the large substituent ends up at the more substituted position. it ends up at the more substituted position because that's where there's a greater amount of partial positive charge. So the electrophile always ends up at the less substituted end, and in this case, since the electrophile is hydrogen ion, the electrophile is smaller than either bromide or water, which means that the large substituent, bromide in this case, hydroxyl group in the case of hydration, is going to end up in the more substituted position. So if you were to do an acid catalyzed hydration with sulfuric acid, 6 molar sulfuric acid in water at a lowish temperature, you would expect to get 2 butanol out instead of 1 butanol. Anytime the electrophile is the hydrogen ion, H plus aqueous, you will get this intermediate carbocation, you will see the Markovnikov regiochemistry, and you will see no stereospecificity because the carbocation is planar. There are 2 other mechanisms that do result in stereospecific reactions that are active for the addition reactions of a lot of other compounds due to carbon-carbon double and triple bonds. And those you go through either a 3-membered ring intermediate with a positive charge on it, or through a syn, and those result in anti-additions, because once the 3-membered ring intermediate is opened, it's opened in stereochemistry, and other syn additions that go through 4 or 5-membered ring intermediates that go in a concerted fashion. Concerted reactions will yield syn additions. We'll see examples of those, but first let's look at the reaction of an alkyne under the same conditions, hydrohalogenation, with aqueous HCl or HBr, and we'll use HCl since we used HBr for the alkenes, and find out what product will be a hydrohalogenation of an alkyne. Because we expect anytime the electrophile is hydrogen ion, that we will undergo a reaction that involves carbocation intermediates. And it turns out that hydrohalogenation of alkynes will result in geminal dichlorides or bromides, where the 2 halogen atoms attach to the same carbon. Comes from the same root as Gemini, the twins. Both of them are attached to the same carbon. And if we start with a terminal alkyne, like propine, and react this with aqueous HBr, we will generate 2,2-dibromo propane. It does go through an intermediate vinyl bromide, but the vinyl bromide is very difficult to isolate. Because as we shall see as we go through the mechanism, the carbocation that results from the protonation of the 2-bromo propene is actually more stable than the carbocation that generates, or that is generated by protonation of propine. So let's take a look at the mechanism. What we expect to happen is for the pi bond of the alkene to attack an electrophile. And in this case, since we're working with an aqueous strong acid, the electrophile is the hydronium ion, as it always is when you're working with an aqueous strong acid. And the electrophile ends up at the less substituted terminal end of the alkyne, generating a vinyl cation. Vinyl carbocations are not very stable. And so that is relatively quickly attacked by a bromide ion to generate the vinyl bromide. And because of the instability of the vinyl carbocation, that reaction is effectively not reversible. You don't undergo subolysis reactions of alkyl bromides. Once you form the vinyl or the 2-bromopropene, it can react with additional acid. And even though this pi bond is less electron rich than this pi bond, because of the carbocation stability, this reaction is faster. Than the initial reaction. And if you look at that carbocation, you can probably tell me why that carbocation is more stable. Because you're probably noticing that there's a empty p orbital containing the carbocation, and the adjacent element, bromide in this case, has a lone pair, which means that resonance is possible. And we can draw a resonance structure that has a positive charge on the bromide, with a double bond to bromine. The resonance stabilization here, even though this is a minor resonance contributor because it has a positive charge on the more electronegative bromine instead of the less electronegative carbon, this resonance structure does more for stabilizing the carbocation than mere hyperconjugation from the sigma system, because we can actually have a pair of electrons moving into the pi bond, which we can't have from the CH3. So hyperconjugation is not as good as resonance. Comes to stabilizing charge. Because this cation is resonance stabilized and this one is not, this is a unstable vinyl carbocation, the second reaction is faster than the first reaction, and that makes it very difficult to stop and not just add the second bromide to make the general dibromide compound. So it's a good way to make geminal dibromides from alkynes, terminal alkynes, if you want. It's not really a very useful reaction for regular alkynes, internal alkynes like this. Right? Well, for this one it would be probably okay. You can make the geminal 2,2-dibromo butane, but if you have 2-pentyne, for example, now there's no preference for which end carbocation would generate, and you would get a mixture of 2,2-dibromo and 3,3-dibromo. So it's most useful when you're working with either a symmetrical alkyne, like 2-butyne, or a terminal alkyne, like propyne, or 1-butyne, or 1-pentyne. So the reactions we talked about in this video are reactions of aqueous strong acids, hydrobromide or hydrochloride. I said I was going to use chloride, but then I didn't. I used bromide anyway. Aqueous hydrogen chloride or hydrogen bromide or hydrogen iodide, or concentrated sulfuric acid in water, which results in hydration because the hydrogen sulfate ion is not nucleophilic. In the next video, we'll consider what happens when we add water across a CC double bond or a CC triple bond, but we don't have a carbocation intermediate. Because the problem with the carbocation intermediate is that you may run into carbocation rearrangements. So let's think about what would happen if we tried to hydrate an alkene that had branching in the beta position, not on the double bond, but next to the double bond. So, for example, vinyl cyclohexane. What would we expect to see as a product of hydration with aqueous sulfuric acid which we know in its first dissociation is a strong acid, so we have hydronium ion and hydrogen sulfate ion. Mechanistically, we would expect the electrophile, which is the hydrodione in this case, to attack or be attacked by the pi bond such that it ends up at the less substituted end and generates the more stable secondary carbocation. We know that the electrophile always ends up at the less substituted end because we always generate the more stable carbocation. But now, instead of water attacking that secondary carbocation, we see that we have a branch in the next position, the beta position, and so we can undergo a hydride shift to generate an even more stable tertiary carbocation. Which means that hydride shift is favorable. And we've just undergone a carbocation rearrangement. The product then, instead of the secondary alcohol, will be the corresponding tertiary alcohol after the next two steps. First, nucleophilic attack to generate, and finally proton transfer to generate one ethyl cyclohexanol. So in this case, we have a four-step mechanism. We have the initial reversible carbonation of the double bond. To generate a carbocation intermediate, we then have the hydride shift to result in a more stable tertiary carbocation. And then we have the usual two steps where we have nucleophilic attack on the carbocation. To regenerate the catalyst and generate the alcohol product. So we've hydrated the double bond, but we haven't undergone a simple hydration of the double bond to generate secondary alcohol. There's no way to stop the carbocation rearrangement. And this is consistent with what we've seen Anytime you form a carbocation, you're subject to carbocation rearrangement. So the question becomes, what can we do if we want to actually generate the secondary alcohol? Is it possible to hydrate that double bond without carbocation rearrangement to generate the secondary alcohol instead of the tertiary alcohol? And even more interestingly, are there conditions that would allow us to generate the primary alcohol, which would be an anti-Markovnikov addition reaction? Is it possible to do an anti-Markovnikov addition reaction where the heavier group ends up at the less substituted end and the smaller hydrogen ends up at the more substituted end? This would be a simple Markovnikov addition. But without the carbocation rearrangement. If we're going to avoid carbocation rearrangement, we have to avoid carbocations. So there must be a completely different mechanism involved in order to generate the secondary alcohol, and again, an even more completely different mechanism involved to generate the primary alcohol, and that'll be the subject of